Welcome to the Deep Dive. Today, we're plunging into something most of us encounter daily, but maybe don't think about too much.
Yeah.
Transportation systems inside buildings.
Yeah, specifically lifts and escalators.
Exactly. We've got some great sources,
Yeah.
including the big one, CIBSE Guide D. Now, this is definitely a guide for the pros, the practitioners. But honestly, it's packed with really fascinating stuff for anyone who's just curious about how we get around inside these buildings.
Right. And we know our listeners, you folks enjoy getting to grips with complex things quickly. You like those aha moments.
Yeah, without the overload.
Precisely. So we've basically done the heavy lifting, sifted through all this material to pull out the key bits. Think of it as your express ride to understanding lifts and escalator.
We'll try and keep the jargon down, keep it clear.
Yeah, definitely aiming for clarity and, keeping it interesting.
And it's worth mentioning the people behind this guide.
Yeah.
Their expertise is just incredible.
Oh, absolutely. You've got Dr. Richard Peters, Dr. Gina Barney, Derek Smith, Dr. Albert So, Peter Day, Chris Chapman, Roger Hawkins, Ish Buckingham.
It's a real who's who from top companies and institutions. Peters Research, Lurch Bates, UMest, Otis, City University Hong Kong.
Land Securities, Trend Control Systems, Ovarup, Elevation. I mean, these are the people who really know their stuff.
So you're getting a really authoritative view here.
Definitely. So our mission, basically, is to pull out the most important, most compelling bits from all this, tailored for you.
Give you that shortcut, that deep understanding of how these essential systems work.
Let's get into it then.
Okay, so where do we start? History, I guess.
Makes sense. You almost have to start with Elisha Otis, right? The famous safety brake demonstration.
Dramatic one, yeah.
Exactly. And what's really striking is if you look at the basic lift components he was working with, the machine, the gears, the sheave or pulley,
The suspension ropes, the guides.
guide shoes, guide rails, the safety gear itself, the car, the counterweight, those core elements are still totally recognizable today.
That's amazing, isn't it? After all this time.
It really is. But if Otis stepped into a modern building today, while he'd recognize those parts, he'd be, completely blown away by other things.
Like what, specifically?
Oh, the drive control, for starters. How smoothly and efficiently lifts move now. Then there's the intelligence, the traffic control, the signaling.
Figuring out which lift comes when.
Exactly. And the monitoring systems constantly checking performance, safety, and just the sheer scale of the engineering and traffic design techniques.
Especially for those huge buildings.
Right. Think Canary Wharf, the Eiffel Tower lifts, Empire State, the original World Trade Center, Sears Tower, Petronas Towers. The challenges there are immense.
It really puts the evolution into perspective.
It does.
Now, something we probably don't think about is that lifts don't last forever. They have a lifespan.
That's right. Typically, you're looking at maybe 15, 20 years before a major upgrade, what they call modernization, is needed.
And that's a big deal for building owners, presumably. A big cost.
Oh, huge. And the guide, section 16, actually gets into this. It provides these economic life factors.
Okay, what are those?
They basically help with life cycle costing, figuring out when it makes financial sense to plan for modernization or replacement based on how long different parts are expected to last.
So it helps make informed decisions.
Exactly. And the guide also suggests a sort of systematic approach to planning and carrying out that modernization. It's complex.
Yeah, I bet. And safety, obviously, has got to be number one.
Paramount. Absolutely. There's a whole raft of British and European standards codes covering everything.
Everything, like from the start.
Yeah, construction, installation, commissioning, the ongoing operation, maintenance. Section 17 lays it all out.
So it's heavily regulated.
Incredibly thorough. It has to be. They cover material strength, safety, circuits, everything. And it's always evolving with technology.
Like the door closing speed you mentioned.
Exactly. There are actual limits on the kinetic energy, how hard they can close to prevent injuries. That comes from learning and setting standards.
Okay, let's zoom out a bit from the lift car itself. How people move around buildings more generally. The guide makes some interesting points, even about queuing.
Yeah, like the assumption for planning is often about 2 people per meter in a street queue.
Which helps designers figure out lobby space, right? Avoid jams.
Precisely. And they talk about different densities of occupation, too. From desirable, which is like 0.4 persons per square meter, lots of space, to comfortable at 1.0, dense at 2.0, then crowding at 3.0, and finally crowded at 4.0 persons per square meter. That's pretty packed.
Gives you a real feel for how space impacts comfort.
It does, and it goes even deeper into, like, interpersonal distances.
Oh, yeah, like personal space bubbles?
Sort of. They mention public distance or the flight zone, that buffer we keep.
Mm-hmm.
Then social distance, far more formal.
Like a meeting.
Right. And social distance, near, which is what you get in denser queues. It shows how our comfort changes with proximity.
Fascinating. And they even quantify walking speeds.
Yeah, and flow rates at different densities,
Wow.
broken down by age and gender to young, middle-aged men, women, elderly people.
So, like, younger men walk faster in less crowded spaces.
Generally, yeah, compared to elderly individuals, for instance, at that 0.6 persons per square meter density, it's detailed stuff.
But crucial for architects planning corridors and lobbies, I imagine.
Invaluable for getting the flow right.
Okay, let's switch tracks to escalators. What are the key things there? Inclination is one, right? The angle.
Yep, typically around 30 degrees. There's a range, maybe 27 to 35 degrees. But speed and the total rise, how high it goes, impose limits.
And the steps are different from stairs.
Very different. The usual stair design rules don't quite apply.
Yeah.
Escalator steps have a longer going, the flat part, about 400 millimeter, and a typical rise of maybe 210 millimeter.
Is that why walking on a stopped escalator feels weird?
That's exactly it. The guide points out that combination is often longer than our average stride. Feels like exaggerated stepping.
Okay, that makes sense now. And widths vary.
They do. Common ones are 800 millimeters, 1,000 millimeter. You also see 1,400 millimeters sometimes.
The wide ones.
Yeah, they can fit two people side by side or let someone walk past on a moving walkway.
And capacity. How many people can they actually move?
Well, theoretically, if you pack them in, it's hot, maybe 4.0 persons per square meter. But practically, it's usually about half that, maybe 2.0.
Still pretty high density, though.
It can be. Passenger conveyors, the flat ones, might even handle slightly higher densities sometimes.
Okay, back to lifts. How do we figure out their handling capacity? There's a formula, right?
Yes, C1 equals 3,600 times P, all divided by INT.
Right, break that down. C1 is?
Passengers per hour the lift system can handle. P is the number of people the car can hold.
And INT?
That's the crucial one, the average interval, in seconds, between lifts arriving at the main floor.
So the waiting time, essentially.
Well, the frequency of arrival. A shorter interval means lifts arrive more often, which generally means less waiting. That INT is often the limiting factor.
So even a big lift car doesn't help much if they don't arrive frequently.
Exactly. It highlights what they call the throttling effect of lifts compared to escalators.
Throttling effect.
Yeah, they inherently limit the flow rate. The guide gives an example. Even an efficient group of 8 big lifts has a maximum hourly capacity. A smaller group, say 3 lifts, is even more limited.
Which is why escalators are preferred for mass transit, like stations.
Precisely. Though, as the guide notes, the way people move in buildings like offices or shops is usually quite different from that kind of bulk transit scenario.
You can't just apply station logic to an office block.
No, the arrival patterns, the destinations, the peak times, they're all different. Needs careful thought for each building type.
Speaking of building types, let's look at some specifics. Shopping centers are interesting.
Very. They often deliberately bend the rules of smooth circulation.
How so? To encourage shopping.
Pretty much. Exits are marked for safety, obviously, but finding your way around might be less direct. You see displays, stands placed to catch your eye, maybe slowing you down.
Interrupting the flow a bit.
Right. And even escalator layouts, that crisscross pattern you sometimes see. Type C in the guide's figure that can intentionally lengthen your route past more shops.
Clever or maybe annoying, depending on your view.
Could be both. Then there are stairs. We use them, but the guide points out limitations.
Like pacing, needing to see your feet, using handrails, and the effort.
Yeah. And crowding levels, again, uncrowded around 0.4 persons per square meter, crowded up to 0.8. Average shopper speed on stairs is about 0.7 meters per second.
Visibility and signage are key then.
Crucial in retail for stairs, escalators, and lifts.
What about car parks? Seems less about people walking inside, more about cars getting in and out.
Exactly. The constraint is usually the ramp capacity and maybe average car occupancy. That's the bottleneck.
And factories. Mostly low-rise. Special requirements.
Often low-rise, yeah. And you might need special provisions like barriers around machinery, things related to the processes inside. Very specific needs.
University campuses sound like a unique challenge. Those lecture changeover times.
Huge peaks. But the guide makes a really good point. Just putting in loads more lifts to handle that short, intense peak is usually not cost-effective.
Because they sit idle most of the time.
Right. They suggest it might be better to look at rearranging the timetable, spreading the load, thinking about managing demand, not just supply.
That's a smart way to approach it.
Yeah,
More holistic.
definitely.
Okay, let's talk lift grouping and traffic design. Putting lifts together in a central core seems to be the recommendation. Why is that better?
Several big advantages. Firstly, shorter waiting times usually, because the system can send the nearest car.
Makes sense.
Secondly, redundancy. If one lifts down for maintenance,
The others can pick up the slack.
exactly. And thirdly, it enables better group traffic control systems to manage them all efficiently.
Traffic design sounds complicated. The guide says the calculations look simple, but the theory is tricky, and you need experience.
Very much so. There are two main approaches: the older, formula-based classical methods and newer, discrete digital simulation.
Simulation sounds more powerful.
It is, especially for complex patterns. Formulas use averages, but simulation models the building, the lifts, even passenger behavior much more dynamically.
You mentioned complex patterns, like lunchtime in an office.
Yeah, in single-tenant buildings, you often get significant two-way traffic around midday, people going down for lunch, others coming up from outside or other floors. It's different from the morning up peak.
Right, not just everyone going up.
No, it needs specific consideration.
And office density matters too. How many people per square meter?
Absolutely. The guide mentions different sources, like the British Council for Offices giving slightly different figures, but that number directly impacts the load on the lifts.
And arrival rates depend on other things too.
Yeah, building occupancy type, start times staggered or all at once, and how close it is to public transport.
So a building near a station might get a sharper peak.
Potentially, yeah, compared to one where people arrive more gradually from different places.
We mentioned round trip time, RTT, before. Can you break that down?
Sure. It's the total time for one lift cycle. So time accelerating, time at full speed, time decelerating, time leveling precisely at the floor.
Door opening and closing time.
Yep, at each stop, time traveling past floors between stops, and the time for the express return trip down to the main terminal. It's quite detailed.
But the guide warns that different companies might define cycle time differently.
That's a really important caution. How they measure it can vary when they start and stop the clock. Whether they include tiny delays for door locking or final leveling, you need to know exactly what their number includes.
So compare carefully.
Definitely. And if there's an express zone like lifts skipping lower floors to serve a higher block, you need to add extra time for that express travel up and back.
Makes sense. The guide has a table, 3.6, for choosing lift speed based on travel time, aiming for 20-30 seconds for the main top-to-bottom run.
Yeah, that's a rule of thumb.
Right.
Balances speed with comfort and efficiency. The table also gives typical single-floor travel times and mentions limits on jerk.
Jerk, like how quickly the acceleration changes.
Exactly. Keeping that smooth is key for ride comfort.
Doors side opening versus center opening. Any advantages?
Center opening doors are often a bit quicker, speeding things up, and the symmetrical movement can mean less car sway.
And door weight matters for safety.
Big time. Standards like BS-EN 81 limit the kinetic energy of closing doors. So heavier doors actually have to close more slowly to stay within safe limits.
Interesting constraint. Some doors just use a timer.
Yeah, fixed open time, basic approach. The guide also mentions using another table, 3.8, to estimate things like H, the highest likely reversal floor, and S, the probable number of stops. Useful early on.
Okay, and there was an example comparing different designs. Aiming for 80% car loading seemed optimal.
Yeah, that often hits a sweet spot between using the list capacity well and keeping waiting times reasonable. But again, for complex patterns like lunchtime peaks.
Simulation is the way to go.
Really, yes. Mathematical analysis gets incredibly difficult then.
And if passenger lifts are also used for goods sometimes?
Protect the car interior. That's the strong recommendation. Scratches, dents.
Makes sense. What about observation lifts? The glass ones in atriums?
Mostly an aesthetic choice in places like hotels, shopping centers, visually striking.
And residential buildings. That interleaved zoning concept.
Right. That's where, say, one set of lifts serves only even floors, another set serves only odd floors.
Why do that?
The idea is fewer stops per lift, potentially faster overall travel, maybe lower initial cost, but
There's a downside.
yeah, service can be less convenient, longer waits for your lift, maybe having to use stairs if you get the wrong one, and people try to game it, call both lifts.
Huh. I can imagine. For low-rise buildings like shopping centers, again, stairs and escalators are more dominant.
Absolutely essential for moving lots of people between fewer levels. In offices, maybe less used for general circulation, but still vital for things like trading floors or connecting to car parks.
And lift lobbies. Central core location is best. Keep walking distance under 45 meters.
That's the guideline, yeah. Minimizes walk time. If a building has multiple entrances, try to funnel people towards one central lift lobby for efficiency.
And things inside the building matter too, like a big canteen.
Definitely. Restaurants, gyms, whatever. They create their own traffic peaks at different times. Got to factor those in.
So many variables. The guide mentions specific considerations for airports, stations, department stores, universities, residential. All different.
Each has unique patterns. The standard up-peak calculation, while common.
It has limits, especially outside offices.
Big limits. It assumes that main morning rush upwards. For more accuracy, especially elsewhere, you need better data. Passenger loading, unloading times, average weight, floor populations, and you need that up-peak handling capacity target. The percentage of the building population the lifts need to move upwards in a 5-minute window. Standard benchmark.
So using up peak calculations for a shopping center or car park is basically wrong.
Pretty much inappropriate, yeah. Traffic flows are totally different.
And the guide is wary of just using built-in traffic analyzers in existing lifts.
A bit skeptical, yes. For assessing current demand or predicting modernization benefits, they strongly recommend doing actual manual people counting surveys. Get real data.
Annual surveys.
Yeah.
People with clipboards counting.
Essentially, yeah. Counting people on-off at the main terminal, or maybe at all landings.
That sounds labor-intensive.
Yeah.
And maybe not perfectly accurate.
It has limitations, sure. Time-consuming, might miss complexities. Example 4.2 in the guide actually compares results from general analysis versus an up-peak calculation for the same building, showing how they can differ on interval, capacity factor, etc.
Highlights the differences in methods.
Exactly. The guide also mentions group control benefits, again, better coordination, shorter waits.
And there are examples for double-deck lifts and simulation results.
Yes. Example 4.5 covers double-deckers, and 4.7 shows results from an up-peak simulation visually in figures.
Okay. Passenger waiting time, that's from pressing the button to the doors starting to open.
That's the definition. And if a system is under design, longer simulations will show those waiting times just creeping up and up.
So you need to simulate long enough to see if it stabilizes.
Right, and feed the simulation consistent, realistic passenger arrival data. Garbage in, garbage out, otherwise.
Makes sense. Finally on this, quality of service. Passengers feel it as waiting time, but it's formally measured by?
Often by the theoretical interval time. Shorter interval generally equals better quality of service, higher handling capacity.
Less waiting, happier people.
Pretty much sums it up.
Okay, let's get into the actual lift system design, the components. The guide makes a big point early on. Lifts aren't an afterthought anymore.
No way. They're a crucial building service now. Can seriously impact rental values, desirability. A bad lift system is a major turnoff.
And passengers judge them on.
Safety, first and foremost. Then smoothness, no jerky rides. Noise levels. And just the general comfort and feel of the car.
Modern systems use microprocessors a lot for more tailored control.
Hugely. Allows very specific tuning of the drive, the doors, the group control logic, adapting it precisely to the building's needs. Much more flexible than older systems.
And different buildings have different needs here too. Hotels need longer door times for luggage.
Right. Shopping centers need bigger cars for trolleys, push chairs, maybe those observation lifts in atria for the look.
And machine room location. Hydraulic ideally at the bottom, electric traction ideally at the top.
Those are the preferred spots, yeah. Generally, simpler installation, easier maintenance. Putting them elsewhere can add cost and complexity.
Observation lifts, same capacity, but might attract sightseers.
Can happen in public buildings, yeah. People riding just for the view, which can slightly affect the actual transport capacity. Less of an issue in private spaces.
Environmental factors matter too. Heating for cold climates, AC for sunny glass cars.
Definitely. Trace heating for exposed parts and frost. AC in glazed cars in direct sun is important, partly comfort, partly preventing heat buildup that could even cause issues or entrapment.
And maintaining those glass lifts. Cleaning access. Hidden machinery.
All considerations need safe access for cleaning. And sometimes the aesthetic covers over machinery can make maintenance access a bit slower.
Accessibility, hearing aid loops, emergency phones. The guide recommends programming the phone to an on-site number.
Yeah, if there's a manned phone on-site, can mean a quicker response, fewer false alarms to external call centers. Practical tip.
Goods lifts designed for materials, not people. Different drives available.
Yep. Hydraulic for a lower rise, slower speeds. Machine roomless electric traction for a bit higher, faster. Rack and pinion for potentially unlimited travel height.
Key factors for goods lifts are accurate floor leveling and low noise.
And crucially, clear access for loading, unloading. Gotta think about the size of goods, packaging, handling equipment like forklifts.
Different entrance types possible too. Straight through different levels.
Adjacent, through, floor level, counter height. Lots of options. And robust doors or gates are essential manual or powered. Pit depth requirements also vary.
They even give examples for fitting vehicles inside.
Yeah, car transport requires specific dimensions. Electric traction goods lifts need machine rooms, similar to passenger ones. Low-rise hydraulics might use twin rams, but borehole costs are a factor.
What about mass climber lifts, often seen on construction sites?
Right. Counterweighted design, safety gear based on hoist standards need regular drop tests.
And explosion-protected lifts, X units.
Specialized, expensive stuff. Best to locate lifts outside hazardous areas if possible. Offshore requirements are particularly demanding materials, coatings, documentation.
Inclined lifts, like funiculars on hillsides.
Yep. Modernization often follows tram or railway codes. Scissor lifts need barriers, load securing. Stair lifts for accessibility, usually chain-driven.
Firefighting lifts critical safety. Need fire-resistant shafts, stairs, lobbies.
Yes. And 2 independent power supplies are mandatory, often with the primary on an exclusive circuit. Regular inspections 6 monthly and yearly.
Escape lifts for disabled people. Minimum size.
Usually 8-person minimum, specific dimensions for wheelchair access.
Then the drives themselves, geared versus gearless traction. Solid-state controls, improved smoothness.
Massively. Geared machines use a gearbox, common for lower medium speed and load. Gearless have the motor directly on the sheave for higher speeds rises, often using special grooves or double rope wraps for grip.
Drive sheave material matters for traction and rope life.
Very important. And sometimes shaft dimensions need to be bigger for bottom drives or counterweight safety gear.
Modernization in old buildings might have space issues, reduced clearances.
Yeah, BS 5655, Part 11 covers that. Might need special permission, a derogation for things like smaller refuge spaces.
Linear induction drives exist, but usually go on the counterweight, due to magnetic fields noise.
That's the typical placement, yes.
Hydraulic lifts, direct acting, ram under car, versus indirect, roped.
2 main types. Guide discusses cylinder piston construction, CILs. Travel and pit depth are critical for indirect types. Controller cabinet usually nearby.
Safety gear instantaneous for low speeds, progressive for higher, activated by an overspeed governor.
Correct. Instantaneous is simpler, limited to about 0.63 meters. Progressive applies braking more gradually. The governor is the trigger.
Ropes have different lays, affecting flexibility, wear.
Ordinary lay, Lang's lay. Subtle differences. Simplest roping is single wrap 1.1. Choice depends on machine position, headroom, load, speed.
Car design, isolated top for passenger lifts, robust platform for goods.
Generally, yeah. Door operators often AC variable frequency now. But doors and operators are a known weak spot, a major source of breakdowns.
Safety edges and photocells on doors are standard now.
Essential. Mechanical, electronic edges, light beams to detect obstructions.
Landing doors hinged, shutter gates, center opening power, vertical biparting for big goods lifts.
Lots of options depending on use. Safety gear is on the car frame and the counterweight too. Always mechanical application, not reliant on power.
Instantaneous gear is simpler. Governor rope system triggers it.
Right. And push buttons height and spacing matter for accessibility. Position indicators in car and landings, lift busy lights for simpler systems. And the yellow emergency alarm button with 2-way comms. Vital.
Okay, moving into lift drives and controls in more detail. The guide aims to be unbiased here. Help with specification.
That's the goal. Help compare options confidently. We mentioned the power controller manages doors based on detectors.
And typical inputs to the controller. Car calls, landing calls, safety signals.
Doorwell interlocks, fire recall signal, emergency power input, maybe bed service in hospitals. Lots of input.
Control logic has evolved, from relays to solid state to computer-based.
Big evolution. Relay logic is declining. Solid state had some reliability issues with connectors sometimes. Now, computer-based or intelligent controllers are dominant, most flexible, most powerful.
Suitable for most buildings and traffic patterns.
Pretty much the standard now. The guide gives a rule of thumb for hydraulic lifts based on motor starts per hour related to oil temperature management.
Speed control. Open loop versus closed loop. Closed loop is better for accuracy.
Much better. Open loop, no direct feedback, struggles with smooth stopping and precise leveling. Closed loop uses speed sensors, position encoders for constant monitoring and adjustment.
With backups against feedback failure?
Usually, yes. Duplicated sensors, monitoring circuits for safety. For electric lifts, VVVF drives are highlighted again, variable voltage, variable frequency.
Energy efficient, accurate control, no DC generator needed.
All key advantages. Smooth torque reversal is important for ride quality. Power conversion uses thyristor bridges, phase control.
Older AC two-speed systems used thyristors and DC braking.
That was a common method. Modern VF drives work with induction motors and increasingly permanent magnet synchronous motors.
Which are even more efficient and compact.
That's right. Constant refinement happening.
Okay, group control managing multiple lifts. Conventional algorithms often target the up peak.
Historically, yes. But flexitime, building facilities, they can shift the busiest pattern. It might not always be the morning rush anymore.
So conventional up-peak control sends cars down, fills them up, sends them off.
Basically, yeah. Cars wait at the main terminal, dispatch when full or after a timer, often express return.
Destination control sounds more advanced. You input your floor before getting in.
Yes, using a keypad in the lobby, it groups passengers going to similar floors into the same car.
Benefits are reduced waiting, faster journeys, maybe higher capacity.
Those are the claimed advantages, yeah. Allows for more optimized routing.
And AI is creeping into lift control.
It is. Representing knowledge about traffic, using it for dispatching, assembling the control logic.
How do these smart systems estimate passenger numbers?
Various ways. Load weighing in the car. Rough estimate. Photocells counting entry-exit, pressure pads in lobbies, even imaging systems with AI analysis. Plus statistical methods like the inverse SP using neural networks to spot patterns.
Clever stuff. The main goal is still keeping lifts evenly spaced. Avoiding bunching.
That's a key objective for minimizing waits. Bunching is inefficient. Early systems used fixed-time dispatch, which could hurt capacity. Modern systems are much more dynamic.
Okay, shifting back to escalators and conveyors for a moment. Starting methods.
Smaller ones might be direct online, quite abrupt. Soft start uses thyristors for smoother acceleration. Inverter start, variable frequency, is the smoothest.
Brakes are critical for holding stationary and preventing reverse movement.
Absolutely vital safety function. And lots of other safety features. Comb plates, side brushes, skirt obstruction detectors, handrail entry guards, emergency stop buttons.
Outdoor escalators need more consideration. Materials, drainage, weather protection, more maintenance.
All necessary due to the exposure.
Electrical safety, again, isolation in machine room, stay-put buttons top and bottom, protective gear at main supply.
Standard requirements. Cable selection and protection are important, especially critical for firefighting lifts.
And lifts need to talk to other building systems. Phones, alarms, monitoring, HVAC, lighting, security.
Loads of interfaces. Needs precise info and scheduling during design and install to make sure it all works together.
Lift well. Lighting needs specified spacing and controls. Machine room environment needs managing temperature, heat, ventilation.
All covered. Heat for machinery might even offer potential for heat recovery sometimes. Ride quality factors include acceleration-deceleration limits, minimizing noise from wind, doors, hydraulics.
Energy consumption VVVF drives are the most efficient, like 50% of a two-speed system.
Around that, yeah. Big potential savings. The guide has examples for calculating yearly energy use for different lift types, even escalators, based on power, usage patterns, etc.
Worth considering for running costs and environment.
Definitely.
Lift monitoring systems, what are the benefits?
Good for passengers, less downtime info. Good for maintenance, efficiency prediction. Good for owners-operators, reliability, safety, cost.
Different levels.
Yeah.
Basic service performance monitoring.
Right. They monitor signals like door operation, motor load, temperature, power status, calls, car position.
Keeping logs.
Yeah.
Remote fault reporting.
Yes. Event logs are standard. Remote reporting speeds up response. Advanced systems give detailed call reports, call numbers, times, floors, response times, distributions.
Car call and destination call reports, too.
Can do, yeah. Provides a really detailed picture of usage.
So data helps optimize performance and maintenance. More proactive.
That's the idea. Move away from just reacting to breakdowns.
And integrating lifts with the whole building energy management system.
BIMS.
Increasingly common for holistic building management. Two main ways. Via a BIMS integrator, using a communication port and software gateway, like RS-232, or a more direct connection to the lift supervisor's second port, often more limited function.
Could even implement a lift management system using BEMS outstations directly.
Possible, but less common currently.
Okay, final stretch. Commissioning, inspection, maintenance. Crucial for these expensive systems.
Absolutely critical for reliability, safety, longevity. Proper commissioning from day one is vital. Quality varies between manufacturers, too, affecting lifespan. Commissioning involves checks during build and install, then a final big test, using standards like BS 5655 or PAS 32.
Correct. Ensures it's installed right and works as specified. Then ongoing periodic thorough examinations are needed. Safe guidelines for lifts, HSE notes for escalators, though may be withdrawn.
These regular checks spot wear and tear, ensure safety compliance.
Essential for catching issues early. Good maintenance maximizes life, prevents breakdowns. Safe working practices for maintenance staff are also vital.
Modernization, improving reliability, looks, performance, energy use, driven by worn parts or tired finishes.
Often, yes. Key areas are the machine, drive, control system, big gains with microprocessors, doors, car, ropes. Maybe even guide rails need checking against current standards.
Those economic life factors help plan modernization or replacement timing using cost calculation methods, depreciation.
All part of the financial planning. The modernization process itself is staged. Pre-planning, checking limitations, concept design, detailed design, specification, tendering, contract, installation, commissioning, final accounts.
Lots of steps. Key considerations at each stage: population movement, structure, compatibility, interfaces, specs, contractor choice.
All need careful thought throughout the process.
And finally, the regulations. Lifts Regulations 1997 from EU directives, PR 98 work equipment, CDM 1994 construction safety.
Those are key pieces of UK legislation covering lift escalator safety, use of work equipment, and construction project safety management.
Defining terms like lifting operation, principal contractor, planning supervisor, outlining duties under CDM.
Yes, clarifies roles and responsibilities for safety during installation or major refurbishment. Clients, supervisors, contractors all have duties.
And a CDM conviction can be used in civil cases.
That's noted, yes. It's a comprehensive framework, and if you hit unfamiliar terms, there's that big glossary in the appendix.
Well, that was quite the journey through lifts and escalators, really pulling back the curtain on systems we use every day.
It's amazing, isn't it? The blend of old principles, like Otis's safety gear, with incredibly advanced technology and detailed design thinking.
They're so much more complex than they seem, and clearly vital for how buildings function, their safety, even their commercial viability.
Absolutely. Not just boxes going up and down.
Hopefully this deep dive gave everyone listening some of those aha moments, maybe a new appreciation next time you step inside one.
And we've really just skimmed the surface of what's in sources like Guide D. If something specific caught your interest, definitely worth exploring more.
Definitely. So maybe a final thought for our listeners.
Yeah, maybe next time you're waiting for a lift or riding an escalator, just take a second to think about all the unseen engineering, the safety checks, the complex controls working behind the scenes.
All ensuring that hopefully smooth, safe, efficient journey.
Exactly. It's a silent testament to a really fascinating field.